Hi everyone. In this video, we're going to expand on the experiment that we were doing in the last testing physics video. I will definitely leave a link for that video if you haven't seen it. But the basic idea was we had this exact setup. We had a spring and we were attaching different hanging masses to that spring. And we were looking for a comparison between how long was the spring when different masses were attached and how much force the spring was applying to this system. We measured that by using both the force sensor and saying, well, if this system is in a nice balanced state, the gravitational force pulling down and the spring force pulling up should be balanced with each other. So we gathered that data, and if we graph this data, so I'm using Google Sheets to graph this data, if I make a scatter chart for this data, and we can also apply a linear fit and show the equation and show all that relevant information. We found a very, very nice linear pattern between how much the spring had stretched and how much force the spring was applying. What we want to do in this video is expand on that a little bit and see how does that relate to Hooke's law. Does this data support Hooke's law? Does it refute Hooke's law? And are there any other experiments that I can do with this same kind of setup that would further increase our reliability of these particular claims that we're making? So let's look again at Hooke's law. So Hooke's law, the claim is that the force of the spring in newtons is equal to this K value that we call the spring constant. This is measured in newtons per meter. And this is basically a measure of how stiff is this spring. So something like the shock absorbers of a car, a very, very stiff spring, that would have a very, very large value for the spring constant. Something like a skinny elastic band would have a pretty small spring constant. And that spring constant K is multiplied by the stretch or compression distance in meters. So how much has the spring stretched or compressed? Now, we're going to be expanding on some of the ideas that I mentioned in the last scientific critical thinking video. And again, I'll put another link for that one if you want to get that background information. But if we want to take our data and compare it to this claim, we have to be careful in exactly what's being measured in each case, because this equation is talking about the stretch or compression distance of the spring, but the measurements we took were of the entire spring length, not just how much it was stretched. So we need to make some small modifications to Hooke's law. So instead of talking about this stretch distance, I can express that stretch distance in terms of the original length of the spring and the full stretched length of the spring. So for example, let's say I have this spring, and under ordinary circumstances, if nothing's attached to it, it has this unstretched length. And then when I attach some mass to it, or when I start applying a force to it, well, now it has this full stretch length. If I want to know how far did it stretch, well, that's just going to be the difference between the full length of the spring and the unstretched length of the spring. Okay. So I can express that stretch distance in terms of the full spring length and the unstretched length of the spring. And we can expand that out a little bit, saying, well, our claim is that the force of this spring is equal to the spring constant times the full stretched length of the spring minus the spring constant times the unstretched length. When we have some set of data with some particular best fit equation, what we want to try to do is compare our best fit equation, which takes all of our data into account, finds the pattern in that data, and we want to compare that best fit equation to our claim. In this case, we are looking at a linear fit. So let's write out these two equations and see how they can be compared with each other. So again, our claim is that the force of the spring is equal to the spring constant times L minus the spring constant times the unstretched length of the spring. Okay. Our data that we have gathered, well, the equation for a straight line is y equals mx plus b. And for this particular best fit, the computer spit out some values for the slope of this graph and the y-intercept of this graph. So our best fit equation is y equals 5.45 times x minus 0.189. Okay. What we want to do is compare our data with our claim and try to assign physical significance to those fit parameters. So if I try to compare these side by side, well, let's look at what did we graph on the vertical axis? Well, we were looking at our spring force. So the quantity that we have on the vertical axis and the spring force, those match up with each other. On the horizontal axis, we have the length of the spring. So on the horizontal axis, that x value, that's going to be the length of our spring. And we want to keep on comparing these values side by side. So if we keep on this comparison going, this 5.45, rather than just being some number that the computer spit out at us, we can now associate that with our spring constant. So by making this comparison, we can make the statement that according to our data, this spring constant, this k value, is equal to 5.45, and the units for these spring constants are newtons per meter. What about this other value on the end, this 0.189 or negative 0.189? Well, notice that if we continue this comparison, that negative 0.189 should match up with the spring constant times the unstretched length of the spring. So according to this, the spring constant times the unstretched length should be equal to 0.189, and this would be in newtons right now, but we'll see that we can rearrange this to get meters for the unstretched length of our spring. Well, if k is 5.45 newtons per meter, we've got the unstretched length of the spring equals 0.189 newtons. If I want to figure out what the unstretched length of this spring is, I can divide both sides by this 5.45. So let's quickly do that. If I do 1.89 divided by 5.45, I'm going to get the unstretched length of the spring is equal to 0.035 meters. Again, plus or minus some rounding. Okay. So that would be only 3.5 centimeters for the unstretched length of the spring. So we can use this data to give a prediction for what is the unstretched length of the spring. Okay. Now, we are going to find a little bit of a discrepancy, because let's say I take all of the mass off of here and I try to identify with the camera, again, I know this isn't the best view, where that unstretched length to the bottom rung there, so not to the bottom hook, but the bottom rung, that looks like it's around, I don't know, just shy of 5, maybe like 4.8 centimeters, something like that. It's a little bit larger than this 3.5 centimeters that we got. And what's actually going on here is this spring isn't fully unstretched. At this point, the rungs are actually pressing against each other, so if those rungs weren't in the way, if those rungs could kind of like move through each other, it would actually try to compress the spring a little bit more beyond this particular length. If the springs could completely relax, it would actually get a little bit smaller than this, and that's what this value is measuring. Using this as our unstretched length of the spring would actually be a little bit off because it takes a little bit of force to even get this thing to start to stretch. If this were at its perfect unstretched length, I need essentially no force at all to get that first tiny little bit of stretching to it. But again, that's not what we're getting here. So as we compare this claim with our data, first, we do still get that our spring force versus spring length graph is a nice linear graph, which matches the predictions of this Hooke's law model. we get this unstretched length that's pretty close in the ballpark of what we'd expect, especially if those rungs are actually pushing against each other and would want to go a little bit more relaxed if they possibly could. But this spring constant here, we got that spring constant is 5.45 newtons per meter. Well, I don't really, off the top of my head, have any idea whether that is a good approximation of what the spring constant is for this particular spring. We don't have anything to compare it with. So, in order to really make any conclusions about whether this is accurate or not, we need some more data. We need some other aspect of this mass spring system, or this particular spring, to figure out whether that spring constant of 5.45 newtons per meter is accurate or not. Okay. Well, it turns out that we can do a new kind of experiment to give us an independent way of measuring what this spring constant is. So let's introduce that new experiment. So again, we have this tentative value for the spring constant of 5.45, but we haven't been able to check our work at all. We haven't been able to verify this. So what we're going to do is another kind of experiment where I have an oscillating mass spring system. So the basic idea here is that if I have some mass attached to that spring, so a mass m attached to a spring with a spring constant of k, then the claim is that the period of this mass spring system, the time it takes to go through one full top to bottom, back to top oscillation, the time it takes for each cycle depends on the mass in this particular way. 2 pi times the square root of the mass that's attached divided by the spring constant. So the idea here is I can set up a new experiment where I attach different masses to this mass spring system. I set it into oscillation and measure the period of motion. So my two variables that I'm going to be measuring are, I can pick which mass I'm using. That's going to be my independent variable. And I can measure what is the period of this mass spring system. That's going to be my dependent variable. And again, we're going to try to look for patterns in this data and compare those patterns against this claim. So just setting up how we're going to take this data, we're going to have the mass of the object in kilograms. We're going to be recording that. And if I'm trying to measure the time for each cycle of these oscillations, doing just one cycle, it's going to be such a short time, especially for some of the very small masses, that we're not going to get a very reliable timing measurement. Just trying to time something with a stopwatch, I don't really trust any stopwatch times that are less than probably around 2 seconds. If it's shorter than 2 seconds, just your reaction rate is going to be not good enough to get a very reliable measurement. So instead, let's look at the time for 10 cycles. And then if I know the time for 10 cycles, I can find the period of the motion, the time for one cycle. And again, that's going to be measured in seconds. Okay. So we're going to try to measure this. I've got a stopwatch here. So make sure my stopwatch is working. All right. So you can follow along with this. I'm going to add different masses to this thing and try to measure how long does it take this thing to go through 10 oscillations. I'm going to lift this thing up. The period of the oscillations shouldn't actually depend on the amplitude of the oscillations, how large the oscillations are. But I'm going to still try to be consistent and maybe lift each one up 1.5 centimeters and then let it go. And we're going to time 1, 2, 3, all the way up to 10 full oscillations. So you can time along with me if you want. So again, I'm going to try to move this so it's only about 1 centimeter up, maybe 1.5 centimeters to get a little bit more motion. And we're going to start timing in 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So I might redo that one just to make sure that this is reasonable, but for the time for 10 cycles, the first time that I got on this one, that seems to be around 3.9 seconds. So again, the time for one cycle is going to be much shorter. The mass that we were using in that one was 20 grams, so that's 0.02 kilograms. But I'm going to just redo that one just to make sure that that was a reasonable measurement, because this is going to be actually the hardest one that we have to do in this. So I'm going to move that up around 1.5 centimeters, and starting in 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3.83. So yeah, I think we're in the right ballpark for this one. That seems to be a repeatable, reliable measurement. So let's kind of average those two. Let's call that 3.87 is approximately the average. So 3.87. So the period, the time for one oscillation would be 0.387 seconds. Again, there's no way that I'm going to be able to measure this just with a stopwatch with my hand, a time that short. So we want to find ways of increasing the accuracy of our particular measurements. Okay, so that was the 20 gram mass. Let's change this for a 50 gram mass. Okay, so the 50 gram mass, so 0.05 kilograms. Let's reset, and I'm going to do the exact same thing. I'm going to move this up 1.5 centimeters. I'm going to do the same thing, measuring the time for 10 full up and down cycles. So 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I got 6.07 seconds, so let's go with that, 6.07. So the period, the time for one, if 6.07 seconds was the time for 10 cycles, the time for one cycle would be 0.607, just the total time divided by the number of cycles. All right, let's add some more mass. So I'm going to add 50 grams. So now we're up to 150 grams. Again, I'm going to try to keep my hand here, so hopefully that's reasonably visible on the video. And let's reset this. So again, I'm going to move this up. We are looking at 100 grams, so this is 0.10 kilograms. And let's see if we can get the time for 10 cycles. So move this up 1.5 centimeters, and 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, so that's 8.35 seconds for 10 cycles, so 0.835 for one. As I mentioned before, once you kind of have your experimental setup, taking more data is usually not too big of a hassle. So let me reset that. So now we're up to 150 grams, 0.15 kilograms. So move this up 1 centimeter, and here we go in 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, so that's 10.23. So the period for the time for one cycle would just be 1.023. Let's do 200 grams. Again, I don't want to overstretch this spring, but I think we should be able to do this one as well. So that's 0.2 kilograms. Let's reset. Move this up 2 centimeters. We'll make sure that's, 1.5 centimeters is what we've been using. So move that up 1.5 centimeters, and 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, so that is 11.69, so the time for one cycle would be 1.169. And let's do one more with another 50 grams on here. So this is 0.25 kilograms. Is this going to be too far off the bottom of the screen? Just barely, no. Hopefully that's still visible enough. Let's reset. Move that up 1.5 centimeters. I don't know why I keep saying 2 centimeters. And 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. So 13.05. So So this one would be 13.05 seconds for 10 cycles. So the time for one cycle would be 1.305. And we've got a pretty good range of data here. So let me get rid of that. Now what we want to do, again, we have this claim, and we're going to compare this against our data. And we want to find a way to compare the pattern that our data makes. We don't want to rely on any one individual data point. We want to look at the pattern made by our entire data set. And we want to look at how that pattern relates to our particular claim. Okay. I can actually rewrite this claim in a slightly different way. Okay. So if I take this square root, the square root of m over k, I can pull apart those two square root values, and I can write this as 2 pi divided by the square root of k times the square root of the mass. Okay. Well, a square root, taking the square root of some quantity, is exactly the same as taking that quantity to the power of 0.5. So let's check this. If we have our claim of the period of this mass spring system equals 2 pi over the square root of k times the mass to the power of 0.5. We want to identify, well, what kind of fit does this seem to match with? What type of fit should we probably be expecting? If this claim is true, what sort of mathematical pattern ought we see in our data if we were to graph mass and the period? Well, it's not going to be a linear pattern because we wouldn't get this exponent of 0.5 in that mass term if this were a linear pattern. It's not a quadratic because then it would be to the power of 2. There'd be a square term in there. But maybe this is a power fit. The equation that we have for a power fit is y equals some constant a times x to the power of b. And if you look at these two equations, they seem to have the same kind of shape to those equations. So again, if this claim is true, we should get a power fit should match our data fairly accurately. So let's actually generate this. So if I look at that column, I want mass on the horizontal axis, and I want the period of motion on the vertical axis. So I can highlight those columns, insert a chart, and let's see if it gets me the right kind of chart. So it looks like a scatter plot. These data points look like they're doing the thing that I want. I have mass on the horizontal axis, I have period on the vertical axis, so that seems to be matching up fairly well. So again, we get this particular set of data. Notice it's good that we got a couple of extra data points because if I only looked at a few of those data points, this might look fairly linear, but if I try a linear fit to this, so if we go to edit chart and I try adding a linear fit, well, notice that linear fit doesn't quite match all the data super well. There's some other stuff going on. It's got some curvature to it. So instead of having this linear fit, let's try changing this to a power series. So again, we've got our power series. We can label this with our equation, and we can show the r-squared value. Okay? Notice our r-squared value is, in this case, it's close enough to 1 that it's in rounding, which is suggesting that this is a very, very good fit with our data. And our data provided this particular mathematical pattern. So our data was that the y quantity, we can read this equation, is 2.54 times x to the power of 0.48. So let's compare our claim with our data from this particular graph. And again, this best fit equation uses the entire pattern from the entire set of data that we got. Okay. Well, what did we put on the vertical axis? Well, that was the period of motion. So the thing I have on my vertical axis, that matches up with the period of motion. On the horizontal axis, we have the mass in kilograms. So the thing that's on my horizontal axis is the mass in kilograms. Notice that these are lining up with each other pretty well so far. If I would have done this experiment perfectly, and this claim were true, you might want to look at what would we expect this exponent ought to have been. Well, if we compare this side by side, you can kind of see that this experiment, if we would have done this perfectly and the claim were perfectly accurate, we would have expected those to match up with each other. So we would expect that exponent to be 0.5. We got 0.48. That's pretty close. Those are in pretty close agreement. And we can even do a percent difference calculation. Let me move this up so I have a little bit more room to work. We can do a percent difference where we can take, the version I'm going to use is the difference in the quantities in my proposed and theoretical quantities divided by the theoretical quantity, what we would expect to get. So I'm going to label that as the true value, and then we multiply that by 100%. Okay. So the difference between 0.5 and 0.48, well, that's 0.02. Our true expected value was 0.5, and then again we have to multiply this by 100%. So if I run through that, 0.02 divided by 0.5 times 100%, we were 4% off. We were only 4% off in this case. That's a pretty good match, seeing as I was, timing this by hand while also trying to, record this video. Again, we could have tried to get a higher accuracy version of the periods by measuring over more and more cycles. So maybe measure 20 cycles to get more accurate values of those periods. All data is always going to have some amount of measurement error. And we need to evaluate whether the discrepancies that we have between our expected values and the values that we actually got, is that small enough that our reasonable sources of error could account for that. But remember, our goal here was to test whether or not this spring constant is actually 5.45 newtons per meter. We wanted an independent way of verifying that. Well, let's continue this side-by-side comparison. So if we have this best fit value, this 2.54, that should match up with 2 pi divided by the square root of that spring constant. So let's see how those compare. Let's say if I put this 5.45 value in for the spring constant, how close would these combinations match? So instead of 2 pi over the square root of k, let's put in our unverified value for this spring constant. So if I write out 2 pi divided by the square root of 5.45, if I plug in those numbers, so 2 times pi divided by the square root of 5.45, when I run those numbers, I get 2.69. So that would have been, if our k value were exactly correct, we would have expected this combination of 2 pi over the square root of k to give us 2.69. We got 2.54. Again, seems pretty close agreement, but let's again do a percent difference. So again, the percent difference here would be the difference between these two values. So the 2.69 minus 2.54, I got a difference of 0.15 over, let's use this as our accepted value, 2.69. Again, there are other ways that you can kind of quantify this percent difference. This should give us a general ballpark value for how close we got. So if I run through that, so 0.15 divided by 2.69 multiplied by 100, I got about 5.6%. So 5.6% off. Once again, there's no such thing as perfect data. any of your data is always going to have a certain amount of measurement noise. No matter how precise your equipment, there is always going to be some amount of uncertainty. So we're generally going to have at least some level of mismatch between our claim and our data. That's just the nature of data. But it is extremely unlikely that we would have had this close of a match, again, only off by a few percent, if we weren't at least onto something with these particular claims. The measurement errors in our data in how I was measuring the lengths of the spring in the previous video to actually get these spring constants, limitations in how accurately I could actually time those 10 oscillations to get the periods of motion. There's only so accurate that we can be in the experiments. We want to always try to minimize those sources of error, but recognizing that those sources of error are present, this is a very good match and strongly supports our particular claims, both for this equation for how the period of a mass spring system depends on the mass and the spring constant of that system, and the previous claim of Hooke's law. This is very often the general procedure for how we actually put some of these models to the test. If I have some model of how I think some phenomenon in the universe works, how the spring force depends on how far I've stretched the spring, or how a mass spring system is going to oscillate with different masses attached to different kinds of springs. When I have some of those models, when I have a proposed model, we want to be able to put those models to the test by using data, by gathering and analyzing data. And this method of generating a scatter plot of some of this data, looking for these best fit patterns, and then using that entire pattern, the entire set of data together to test out various aspects of these claims. What exponent do I get in this equation? What coefficient do I get in front of my x term? What do I get for these values for capital A and capital B? These models make predictions that we can then go out and test and see whether or not our data supports the claim or refutes the claim. And again, in this case, since we were quite close with, again, only being a few percent off in both of those cases, I would say that this data fairly strongly supports both of these claims. We're going to see these methods applied more and more in this testing physics series, and in the scientific critical thinking series, we're going to be going into more methods of how we can analyze this kind of data in new and interesting and useful ways. So, as always, thank you for the view. If there are questions in the comment section, I try to answer those as often as I can, but have a good rest of your day.